Okay, kids, we're back. We're going to move into chapter 4 now. And chapter 4, we are we're still studying motion. All right, but we're going to study motion in a different way now with different methods. And these methods are called energy methods. Now, energy methods are less reliant on vectors, more reliant on scalars. So we have here what we've just finished studying, kinematics and dynamics, and it was a lot of vectors in it. Velocity vectors, acceleration vectors, force vectors, position vectors, displacement vector. A lot of vectors to study motion in the kinematics dynamics way of studying motion. The energy method way of studying motion is more scalar. There's some vectors involved, but not as much. And we're going to use new quantities, and I'm going to introduce them to you right now. And then as the lessons go on in this chapter 4, we'll go through each one of them and learn them in greater detail. So I'm just giving you like a vocab list right now, vocabulary for energy methods. So we're going to be using things, for example, called work, energy, kinetic energy, gravitational potential energy, and power. And I put the symbols in here. The symbol for work is W. Symbol for energy is E. Symbol for kinetic energy is E subscript K. Symbol for gravitational potential energy is E subscript G. Some people will write it as E subscript P. Doesn't really matter. And power is P. So I've attached a video for you to watch, cartoon kind of video. You guys know I like cartoons. I hope you like them too. We've seen some of these videos before, and it's a really good way to introduce you to uh, today's main topic, which is the concept of work. The symbol is W, and the unit is the joule, big J. And it is a quantity that we need to learn about if we are going to study motion with energy methods. So we're going to look at this new quantity called work. So what physicists will tell you, what scientists will tell you, is that work is being done on an object when a force is applied to that object through some displacement. So the object is moving, and while it's moving, a force is being applied to it. So here's a diagram of that. Here's a free body diagram. Force is applied to it while it's moving through a displacement. Now, how do we calculate work? Well, work is a very special type of multiplication. So it's called a dot product type of multiplication, where we multiply vectors in a very special way. It is also known as the scalar product. So how do we do that? Well, we say that work is equal to the dot product. See how I wrote a dot there? The dot product, or the scalar product of these two vectors. The force that was being applied to the vector, excuse me, the force that was being applied to the object, dot product, scalar product, the displacement vector. And when you multiply these two vectors together, you end up with the scalar known as work. That's why it's also known as a scalar product. Two vectors multiplied together to give you a scalar. So it's a very special type of multiplication. So far, we've been dealing with vectors, and we've learned that you have to add vectors in a different way. And we learned vector tip to tail addition. I gave you a whole recipe for how to do vector tip to tail addition. It involved Pythagoras. It involved finding the tan inverse of the angle and things like that. So here is the recipe for multiplying these vectors together with the dot product, so you end up with a scalar called work. This is what you do. You take the magnitude of the force vector, you multiply it by the magnitude of the displacement vector, and then you multiply those two there by the cosine of the angle between them. So let's look at the diagram. Here's the force vector acting on this object here. Here is the displacement that that object underwent. And theta is defined as the angle between them when we put their tails together, right there. And here's the recipe for finding it. So it's not just 2 times 3 is equal to 6. It doesn't work like that. So let's do an example to help you better understand this. So calculate the work done by these forces. So let's say we have a book here, and the book is on some surface, maybe a countertop, what have you, a table, and someone applies a completely horizontal force to the book, and we're going to call that force push. We're going to call it force push. And let's draw a free body diagram about what's happening here. Okay, let's draw a free body diagram about what's happening here. So we draw the book. Here's the book. There's the book. I've drawn it. There's the force of gravity acting on the book. Okay, force of gravity, also known as weight, is equal to the mass of the object times the gravitational field strength near the surface of the Earth, negative 9.8 newtons per kilogram. There's the push force, and let's say the push force is half a newton, 0.5 newtons. There's the normal force. The book is being supported by the surface. It's not falling through the surface. So we know that the normal force is equal in magnitude, but opposite in direction to the force of gravity. So force normal is equal to negative force gravity. And here is the force of kinetic friction working against us as we push the book. And we know that the magnitude of the force of kinetic friction is magnitude force of kinetic friction is equal to mu k. Let me redraw that. That's better. Mu. It's a mu. Mu. Mu k. Okay. Mu k times the magnitude of the normal force. And let's say that as this object is being pushed this way, okay, um, it is moved 2 meters forward, or positive 2 meters. So this push force works on it with 0.5 newtons while the object moves for positive 2 meters. And let's also say right here that as this push is happening, the acceleration is equal to 0. So it's not speeding up, it's not slowing down during this 2 meters worth of pushing. So let's go through and calculate work done by the push force, work done by force of kinetic friction, and work done by the force of gravity, and work done by the normal force. So here we go. So force push dot the displacement is how we calculate the work done by the push force. And the recipe is we take the magnitude of the push force, the magnitude of the displacement, and the cosine of the angle between them. Well, we know the push force is 5 newtons, excuse me, 0.5 newtons. We know the displacement is positive 2 meters. And if you take a look here at the free body diagram, the push force is this way to the right, and the displacement is also that way to the right. They're parallel. That means the angle between these two vectors is 0. They're parallel to each other. So we write down cosine of 0. Then 0.5 newtons times 2 meters becomes 1 newton meter. And the cosine of 0 is 1. So the work done is 1 newton meter, but we don't write it like that. We now are going to say that a newton meter is equal to the new unit called the joule, 1 joule. Let's do the work done by the force of gravity. So the work done by the force of gravity is force of gravity dot product of the displacement. And the recipe for that is magnitude of the force of gravity, magnitude of the displacement, times the cosine of the angle between them. Well, I haven't been given the mass, so how am I going to calculate the force of gravity? Gee, I don't know. Well, let's continue. Let's put in cos of 90. And the reason I'm putting in cosine of 90 is if you take a look at this, Here is the direction of the force of gravity. It's straight down, vertical. Here is the direction of the displacement vector. It's straight across, horizontal. The angle between vertical and horizontal is 90 degrees, so I can put in cos 90. Maybe that'll help me out. What's the cosine of 90? Well, the cosine of 90 is 0. So I don't really need to know the force of gravity on the object because 0 times anything is 0. So 0 joules. So the work done by the force of gravity, 0. Didn't do any work on the object. How about the work done by the normal force? Work done by the normal force. Well, by definition, work done by the normal force is equal to normal force dot product the displacement, which the recipe becomes magnitude of the normal force, magnitude of the displacement vector times the cosine of the angle between them. We'll look at the free body diagram. Normal force is upward, completely vertical, and the displacement is horizontal. Well, that means the angle between a vertical vector and a horizontal vector, 90 degrees. And cosine of 90 is 0. So even if I don't know the normal force, it doesn't matter. 0 times anything is 0. 0 joules. The work done by the normal force is 0. Let's continue. Work done by the force of kinetic friction. Well, the work done by the force of kinetic friction, is equal to force of kinetic friction dot product of the displacement, which we now know is magnitude of the force of kinetic friction, magnitude of the displacement, and the cosine of the angles between them. Well, the angle between them is 180 degrees. Let me show that to you. The displacement vector is forward. The force of friction vector is backwards. So the angle between here, forward, and all the way over to backwards, right? It's half a circle, all the way over, is cosine of 180 degrees. Cosine of 180 degrees. So uh, at this point, I don't know what the force of kinetic friction is. I don't know that. I have to do some work. So that's where I'm going to use Newton's second law. I know that F net is equal to the sum of all the forces. So F net is equal to the force of gravity, the normal force, the force of kinetic friction, and the force pushing. Those are all the forces working on it. Normal force and force of gravity cancel out as they've done so many times. F net is equal to ma, mass times acceleration. So now I have mass times acceleration is equal to the force of kinetic friction plus force push. But we were told that the object had 0 acceleration. Therefore, mass times 0 is 0. So I have 0 is equal to force of kinetic friction plus push force, which I can then say, look, I'm going to bring push force over to the other side, and it becomes negative push force is equal to force of kinetic friction. So now I know that the force of kinetic friction is equal in magnitude but opposite in direction to the push force. So if the push force was 0.5 newtons, the force of kinetic friction is negative 5 newtons. So now I can go back into here and say, oh, okay, force of kinetic friction, displacement, their magnitudes times the cos of 180. So force of kinetic friction is negative 0.5 newtons. Doesn't really matter. It's between magnitude signs, so it's going to become positive here. I put in negative 0.5 newtons, but it's in magnitude signs. Magnitude eliminates the negative. Displacement plus 2 meters. The cosine of 180 is negative 1. So when I multiply all this together, I get negative 1 joule, with the negative here from the cos 180 giving me the negative sign, not from here. All right, so we've now calculated the work done by all of the 4 forces acting on this object. Okay, next main idea for today is the following. When a force does work on an object, so a force pushes on an object through a displacement, work is done on it. What a physicist, a scientist would say is energy is transferred to or from that object. There's been a change in the energy of the object. So this right here is a hugely important equation. It's right up there with Newton's second law. Massively important equation. That when you do work on an object, you are changing that object's energy. Work is equal to change in energy. Now this work or this change in energy, as you saw a few moments ago, it can either be a negative quantity, like when the work was done by the force of kinetic friction. It can be a zero change, like when work was done by the normal force or work was done by the force of gravity, or it can be a positive change. Energy is given to the object, like the force or the work done by the push force, work push. Positive means energy's been given to the object. Negative means energy's been removed from the object. The push force gave the object energy. The frictional force took energy away from the object. And last here, we have work net, which is equal to the work done by all the forces acting on the object added up, sum of all the works. Work done by the normal force, work done by the force of gravity, work done by the push force, work done by the force of kinetic friction. We know these two are zero, so they're gone. So it would just be left that the work net is equal to the work done by the push force plus the work done by the force of kinetic friction, which we know work done by the push force is positive 1 joule plus work done by the force of kinetic friction is negative 1 joule, so it's 0 joules done. But we also can say that work net is equal to F net times the displacement. Work net is force net times the displacement. Well, didn't we just realize that uh, F net has to be 0 because the acceleration is 0? That net force is 0. So look, 0 times anything is 0. So once again, we get the same result. Work net is 0 joules. Well, that's it for today, kids. I've left you a video to watch, a cartoon video. Hope you like it. I've given you some reading to do and some homework. Stay safe. Do your work. Thanks to all the kids who have been corresponding with me and being active. If you're not that active on this website, I please ask you to become more active. Have a great day. Bye-bye.